Welcome to the Crazy Hat Chemist. So another video here on solubility. So let's get moving. Bam! So today we're talking about solubility example number 10. Already on number 10. So solubility and the dependence on pH. So we're going to calculate the ammonia concentration necessary to begin precipitation of iron 2 or ferrous hydroxide from a 0.0028 molar solution of iron 2 nitrate, ferrous nitrate. The solubility product constant for iron 2 hydroxide or ferrous hydroxide is 1.6 times 10 negative 14. And the constant for the base ammonia, that's a Kb of 1.8 times 10 to the negative 5. All right. So we do know that iron nitrate is a salt, as we looked in the previous problem. Okay, and we have a 0.0028 molar concentration of iron nitrate. We are interested in the common ion here between the iron hydroxide and the iron nitrate. And that would be the same as the iron nitrate. Okay, that's 0.0028 molar for the iron ion concentration because salts dissociate 100%. I know that nitrate is a salt because it is one of the soluble salts. Now, this is the KSP expression for the iron 2 hydroxide or the ferrous hydroxide. That is KSP is equal to the iron ion concentration times hydroxide ion concentration to the power or the exponent of 2. Okay, and so we do have the KSP value, that's 1.6 times 10 to the negative 14. We also have the iron ion concentration. Now what we're going to do is we're going to be solving for the hydroxide ion concentration here. So we got our 1.6 times 10 negative 14 for the KSP. We got our iron ion concentration at 0.0028. And we're going to solve for the hydroxide. Notice that there's still that squared term on the hydroxide. So the hydroxide ion concentration is 2.4 times 10 to the negative 6 molar. Okay, now we're going to write the equilibrium for the ammonia and the dissociation of ammonia. We learned this way back in a previous unit here when doing pHs. So ammonia plus water, and I need to write the conjugate acid-base pairs for the ammonia, the conjugate acid, the conjugate base for water. That will give me the ammonium ion on the product side and hydroxide ion on the product side. Okay, hopefully that works out well for you. We got an ICE table that we're going to do where it's the initial, the change, and the equilibrium here. Okay, we're going to solve here for X because we're trying to get the ammonia concentration necessary here to begin precipitation. So we don't have to worry about the water because that's a liquid and liquids are not involved in any kind of K expression whatsoever. Okay, so the change also for the water, don't have to worry about it. That equilibrium for the water, we don't have to worry about it because it's a liquid, so we're just deleting that. Okay, we don't have anything for the ammonia ion concentration. Okay, that's going to be 0. We don't have anything for the hydroxide ion concentration here initially. But this hydroxide ion concentration is what is going to go here at the equilibrium position. So I'm going to put that right there. So that's 2.4 times 10 to the negative 6 molar. Now the question is, how did I get from the initial of 0 to an equilibrium of 2.4 times 10 to the negative 6? How did I do that? I had to add 2.4 times 10 to the negative 6. Now, knowing that I had to add 2.4 times 10 to the negative 6 to get to the hydroxide ion concentration, that tells me what I need to do for the ammonium ion. I have to add 2.4 times 10 to the negative 6 for the ammonium ion. And that gives me the ammonium ion concentration at equilibrium as well. I'm going to have to subtract that same value, 2.4 times 10 to the negative 6, to the ammonia, because the ammonia is on the reactant side and it is decreasing in concentration because the reaction is shifting to the right. So it's going to be X minus the 2.4 times 10 to the negative 6. All right, so now I have all my equilibrium values. Okay, you should be able to plug this into the appropriate equation here, which is a Kb, and I know it's a Kb because the hydroxide ion is a base. So that's products over reactants with the stoichiometric coefficients as exponents. I got my Kb. The Kb was given to me at 1.8 times 10 negative 5 in this problem. I'm going to plug in these values that were in equilibrium right into this equation, and this is what I have. On the left-hand side, I got 1.8 times 10 negative 5. On the right-hand side, I have the ammonium ion concentration and the hydroxide ion concentration, those two being the same at 2.4 times 10 to the negative 6. In the denominator, it is x minus 2.4 times 10 to the negative 6. Now we're going to do a little bit of a simplification here. Okay, now you cannot get rid of that x term. We've been talking about getting rid of that x term by taking 100 times the K value. Is that less than the initial concentration? But that is when you had a number minus the x or a number plus the x. This time it's the reverse, and it's the x minus that number. We are actually solving for x. If we got rid of that x, we wouldn't be solving for anything. That's another way to look at this. So I am solving for x right here. I cross-multiplied here, and I got 1.8 times 10 negative 5 times the quantity x minus 2.4 times 10 negative 6. That's on the left-hand side. On the right-hand side, I got 2.4 times 10 to the negative 6. That's squared. That's the ammonium ion concentration times the hydroxide ion concentration. Again, some distribution here and a little simplification here. On the right-hand side, I squared that term. On the left-hand side, I distributed the 1.8 times 10 negative 5. Now what we need to do is combine our like terms here, and that's what I've done right here. So the x's are on one side, the non-x's are on the other side with a subtraction addition problem, if you will. Now we're going to divide both sides by our coefficient in front of the x to solve for x. And now I have my solved x term, which is 2.7 times 10 to the negative 6. So, what is 2.7 times 10 to the negative 6? That is the molarity. And where do I place this here? What have I solved for? I have solved for x. What is x? X is the ammonia ion concentration. So the ammonia ion concentration is 2.7 times 10 to the negative 6 molar. Let me delineate this a little bit more. The concentration of the ammonia, that is the NH3, must be just above this value, that is 2.7 times 10 to the negative 6, in order to begin precipitation. So it could be 2.8 times 10 to the negative 6 would be an appropriate value, or 2.7001 times 10 to the negative 6 would also be an appropriate value. Anything greater than this. This is a very complicated problem. It's including common ion effect, it's including solubility, and it's including pH. You need to redo this video and try to do this problem all on your own. I got a great hat here for you in just a second, because I am the crazy hat chemist, and I got a great hat. Absolutely. I am the pharaoh of chemistry, or the king of chemistry, hopefully, if you will. Okay? Give me a thumbs up if you like that video. Please subscribe to my YouTube channel, and please pass on my YouTube channel to all of anyone that you know that needs chemistry help. Here is the place to come, the Crazy Hat Chemist. I'll see you next time. Bye for now.